Well, I lost half the audience, which is a bit of a shame.
We'll trick it back.
Just test this out. So it was interesting listening to the talks this morning because I'm pretty sure I come from the extinction event, like right in the middle of the extinction event. My research is all about understanding geophysical expressions, about integrating different data sets.
I thought you were going to say you're the crappy data guy. No,
So you know, I'm kind of someone that doesn't really exist apparently. It said I was going to talk about, you know, how do you go back here? Yeah, the geophysics are indeed the future, but it's really magnetics I'm mainly going to talk about, and a little bit of gravity. But regardless, you know, with geophysics, you can probably separate it out into four sort of main areas, and that would be data, processing, constraints, and interpretation. And I'm going to talk mainly about constraints today, but I'll come back to this later, and I'll give you a few of my thoughts on where I think we're going wrong. I've been sort of heading up a project over the last sort of year, where we've gone to 20 different deposits in the Cloncurry area. We've sampled sort of between 30 and 80 samples from each deposit based on drill core. And we've basically come down to little cores like this. And we can use these cores to measure a whole bunch of different parameters. So we can measure magnetic anisotropy, we can measure remanence, susceptibility, density. We can take the same samples and we can look at mineralogy. We can look at micromagnetic field mapping, hyperspectral, and micro-CT, any other number of techniques you could use as well. But mainly looking at petrophysical properties and mineralogy in this particular study. So the idea is we start at this scale, and then we take the knowledge up to the deposit scale, and then hopefully at an inlier-wide scale we can build up a framework, which we should then be able to take undercover to assist exploration undercover. So that's the basic theory. So I'll just give you some of the outcomes, and then I'll give you an example from one of the deposits. So this is basically the inlier. These are some of the deposits, and I'm just showing here the AMS data. So AMS stands for anisotropy of magnetic susceptibility. So what we're seeing here is actually fabrics measured at all these different deposits. And what you can see is you're getting this north-south fabric at most deposits, particularly in some of the older SEDEX systems. They've only really seen that D2, they're not affected by the later D3, D4, etc. Most of the larger IOCGs are affected by the D4 and the D3. And you can see these here, like things like Monacoff, Ernest Henry, for example. That's just an example anyway. But basically what it allows us to do is to basically take all this data, put it in a sort of a spatial framework where we can look at not only fabrics but alteration styles, mineralization styles, etc. We can also put it in a temporal framework, and I'd have to say there's maybe a little bit of guessing going on in here because you need to have all of the geochronology to go with this. But nonetheless, we can take all of these results from all of these deposits, put them in a temporal framework, and there's quite a lot of similarities between the different deposits. So I'll just quickly say, I think this is a way we can actually do this better. It's basically doing things in a consistent manner. So taking the same size samples, doing exactly the same techniques on them, and that way you get to the end of it and you have a consistent data set. And I think that's probably one of the main problems with the data we have at the moment is that it's just so bloody inconsistent. There's so many different techniques, it's been done at different times by different people, different outcomes. So I think one of the ways that we can do things better in the future is by doing things much more consistently. So I'll just give you a quick example of some of the outputs. This is from Ernest Henry. So I'll just start here with, this is just the first VD magnetics. So you can see here the sort of classic Rick Valenta sort of thrust job sort of system here. But I'd also point out that there's quite a number of offsets running through the middle here, and these seem to control where the magnetite is. And I'd also
are those actually documented in the field, or are they just on the net?
Oh no, you can measure that. I'll show a slide later. I've actually measured the fabrics in them. And yeah, Ernest Henry seems to basically sit at the intersection of part of that thrust system with a north-south fault. Okay, so this is just an example of some of the data we've collected here. So this is TEMA data, T-scan integrated mineral analysis, I think it stands for. It's basically electron microscope, and then just based on the spectra, they can figure out the mineralogy. There's a bit of a key up here and up here. So what you're seeing here, you're seeing basically from the top of the drill hole right through the system down into the bottom. The light blue here is albite and magnetite and titanite, so you're in a sodic system here. As you go into the ore zone, you get into this sort of proto-breccia. You can see the dark blue here is calcite, the orange is K feldspar. When you're in the middle of the system, the mineralized system, the two bits that you have are these potassic altered magnetite-rich rocks, and then you have these sort of breccias there, where you basically have quartz, calcite. So this is actually overprinting the host rocks, and this part of the system is actually overprinting them. And I'll show you a bit more about that in a second. And then as you get into the bottom of the system, it's just a potassic alteration. It's much more sheared fabric. And here you basically just have an altered volcanic. And you can sort of see where these samples come from in the downhole section here. Unfortunately, I have to just flash this up really quickly and move on. Yeah, it's quite spectacular data, and we have like 800 samples of that, just that data. So you basically have an encyclopedia of all the different rock types in these mineralized systems. So we've also been doing magnetic modelling. So just trying to relate what we've just seen there. So these red zones here, the shear zones, they're basically the magnetic highs in this system. The light blue here is the breccia, and the sort of darker blue as well is the breccia. So that's less magnetic, but still magnetic. And if you go into the main mineralized system, that has much more quartz, calcite, and hematite, and that's actually, it's a relative magnetic low. So everyone would say that Ernest Henry's a magnetic anomaly, but in fact, the mineralized part of the system is a magnetic low relative to the rest of it. And even the Glencore geophysicist working up there, who's a good guy, smart guy, he's trying to model the ore pipe as a high, and he's been wondering why he couldn't do it for the last year. Another thing to show here, so basically I've separated out the different samples by different alteration type here. So you can see they're pretty much all plot on the magnetite trend here. The only ones that don't is where you have these basically calcite, chlorite, hematite, pyrite alteration in here. They're sitting below the magnetite trend, and that's basically because they've got pyrite, hematite forming. So these are getting oxidized relative to the rest of the system. So I was telling you about the AMS studies before. So AMS is just a way of measuring the magnetic fabric, essentially. So what you can see here is basically the K1. That's the K1, so that's the main elongation direction. That's the intermediate, and that's the K3. So that's the more or less the shortening direction, if you like. If you draw a great circle between K2 and K3, that's basically the foliation. So that's like the magnetic fabric. So what you can see here is that in fact you've got a fabric dipping down to the southeast, which is what you were asking for, and that basically fits the classic model for Ernest Henry. In the breccia here, all the fabrics are completely random, and you'd expect that. And then if you get into the sort of quartz, hematite, calcite altered samples, they basically, show a north-south upright foliation. And the K1 being down here, that basically means that this is like a strike-slip system. So even within this deposit, you can figure out different structural fabrics that are basically controlling different types of alteration. And you see here, so the main K1 lineation is sitting at the intersection of this thrust plane with a north-south strike-slip fault. So it all makes sense. So just trying to bring some of this together in 3D. So this is from the Mag modelling here. You've got the footwall shear zone. That's the Marshall shear zone. This is a leapfrog model here of gold grade. So you can see that that's basically plunging down subparallel to the footwall shear. But it's also to some extent picking up the Marshall shear and some other random structures down here. So I think basically it's fairly consistently showing that the mineralisation is picking up the main structural fabric here, but it's basically controlled by the north-south fault. James might disagree with me on that. So yeah, I just want to talk quickly about what actually restricts our ability to predict. We'll make this interactive if you like. So I'm just going to show you a few slides here. So this is a magnetic anomaly. Where would you drill there? Anyone?
I wouldn't drill there.
No?
No, I want to see what other data we have available to make a decision.
If you had to drill.
Well, I mean, obviously,
I still wouldn't drill.
the gut reaction is to drill where it's strongest.
Yeah. So most people would probably
I
say
don't think my
drill.
target's magnetic positive or magnetic negative, so I can make a decision on where to drill.
Stop ruining my interactive session.
But it's
Most people would say that. If you were exploration manager 5 years ago, you would just go and drill there. Trust me, that's what my exploration manager would have done. So that's basically fairly normal resolution magnetics. Okay, if I showed you this, it's the same area. What would you say then? Probably say the same thing. Go to a bit of a first VD on it. It actually starts to look completely different. You're starting to get this folded structure here. You've got truncations through here, and you're actually starting to see something that looks like it could be a SEDEX deposit or something, which in fact it is. So I guess one of the interesting things here though is that this is highly magnetic up here in the north, highly magnetic here in the south, very weakly magnetic here in the middle. And that's where all the ore is, in the middle, basically. And calcite, interestingly enough, I think someone mentioned, was it before calcite?
Yeah.
We're wasting our time drilling calcite. It's just calcite, pyrrhotite and galena, a whole lot of it in there. So I think the point I'm trying to make there is you've got something very simple there. You go and get better data, you can actually start to recognise the geological complexity here. And I think I'll come back to that in not too long. So that's just, this is just basically the magnetic model in grey here, and that's the leapfrog interpolations of lead. I've also got silver, zinc, and these sort of round cylinders here. That's just a model based on the regional data. So you can see there's quite a bit of a mismatch there between what the regional data is telling you and what's actually going on. And I think that's quite common in everything that we do. So just thinking about remanence again. So in the middle of that system, it is magnetic, but it's dominated by pyrrhotite. So rather than having a high susceptibility, it has a really, really low susceptibility and a very high Königsberger ratio. So Königsberger ratio of 60, I think it is. So the magnetization in that middle part of that system is high, but it's just not in the same direction as the rest of it. So it has a subtle magnetic feature. And actually for the whole study, it's quite common. A lot of these systems have very high Königsberger ratios. So remanence is very significant in a lot of cases. And if we think about doing unconstrained voxel inversions, for example, they basically don't take remanence into consideration at all. And it's something that we should be doing. Okay, so I'll just give you a quick example of gravity again. So this is just a gravity grid over a certain area of Australia. And here it's basically, it's a sort of a more or less an 8 kilometre grid, which is pretty common through most of Australia. Probably 50% of Australia would have 8 kilometre gravity, and probably most of the rest would have either 4 or 2 kilometre gravity. So none of it's particularly high resolution, but it's a big country, I guess. So I mean, if I showed you that, would you want to drill there? No. Would you even look at it twice? Oh, it's a leading question.
I'd like a scale bar, please.
Well, that's about 8 kilometres.
Yeah.
Oh, okay. It's run-of-mill gravity.
Okay, if I showed you that, which is exactly the same area, but with the high resolution gravity, then it becomes a bit easier, doesn't it? So this is actually basically the Olympic dam area with 8 kilometre gravity. So the point is, obviously, if you can hide Olympic dam in 8 kilometre gravity, what else can you hide in that sort of spacing of gravity throughout Australia? Or what can you hide in 2 kilometre of gravity? The answer is quite a lot. And I think we need to be thinking about this quite a lot more. So just coming back to my sort of pie chart originally. Okay, I think we're collecting data. I'll come back to that later. I think we're collecting data the same way we've been collecting it for a long time. And I think I'll talk about that last. Processing. I think we spend most of our time, and most of our academics spend most of their time doing processing. And I would throw voxel inversions in there, for sure. I think why we do this, it's fun for people who like physics and maths. They can do it on computers in offices and don't have to get their hands dirty. But we're really just creating more data, more and more and more data, and it doesn't actually really help us. Constraints. This is actually really hard. It requires specialised equipment. It's labour intensive. The interpretation can be quite hard. And almost nobody's doing this work, but I remember being at the Uncover Symposium in 2014. Everyone was standing up saying we need to do more petrophysics, but nobody's actually doing it. So it's just because it's too bloody hard. But it is actually really insightful, and this is actually really what limits our ability to interpret properly. Interpretation, you talk to most people and they think, with magnetics, interpretation is drawing lines on maps. And it more or less is for most people. Integrating petrophysical constraints is quite difficult, but it should be done. And I think the big key, and you were alluding to this, other data sets always need to be incorporated into the process. And that's where I think, not having geophysicists in exploration teams is actually a big problem, because they don't have people there who can oversee the process from start to finish. If you're working with consultants, what happens a lot of the time, you get a product from the consultant, give it to the geologist, they say, okay, there's the target, we're going to drill that, and that's the end of it. And I think that's a big problem. I think with data, it hasn't changed for a long time, and I think this is where we can really affect a step change here. With things like rovers or drones, we can actually start to create new data sets, high-resolution data sets remotely. And I think this is basically data limits how our results are going to end up before we even start any of this process. And I think that's basically the key, and that's what I've seen working on this project over the last sort of year and several other projects. It's not really what we do with the data that matters. It's often the data itself is what is letting us down. So for me, future in R&D in geophysics, in particular magnetics, I think it needs to be a lot more work done on understanding what these systems look like, for one thing, but also a lot more work on figuring out how to get much better data sets. And I believe that is it.
Thanks, James.